So let's look at this example problem, and we're going to use a strategy to figure out what our fundamental frequency is. And so it says a tube has successive harmonics at 240 and 400 hertz. Is the tube open or closed, and what is the fundamental frequency? And then see what is the tube length if its diameter is 0.05 meters. All right. A and B are very closely related to each other. This is how I can analyze and figure out what's going on. So I'm going to say that my first one is Fn. The first frequency I'm given is 240 hertz. That's what it says. And then it says the next successive harmonic is 400 hertz. But I don't know if the tube is open or closed. If it's open, that means Fn plus 1 is my next harmonic, and that's 400 hertz. However, if it's closed, remember I don't get to add 1 to that, I got to add 2. I go 1, 3, 5. So this is F3, the next one's F5. This is F5, it's F7, which means if it's a closed tube, it's plus 2, not plus 1. Okay? So I don't know if it's this way or that way. So I've got to try it. So what I'm going to do is I'm going to say, well, the nth harmonic, Fn, is given by the fundamental times n. And that means the next harmonic, Fn plus 1, is given by the fundamental times n plus 1. And in this case, that's Fn, F1n, plus F1. So what I have is Fn equals F1 plus n, and Fn plus 1 is equal to F1n plus F1. Well, if I take and subtract this equation from that equation, what I get is F1, which means if I take 400 minus 240, I get 160, which is F1. However, that's a problem, because if F1 is really 160, then there is no n, no integer I can multiply by to get to 240, which right away tells me this is not an open tube. So I can try again, but this time I'm going to use the fact that a closed tube is going to be F plus 2. So I still have Fn equal to F1 times n, and now I'm going to check my Fn plus 2, which is going to be F1 times n plus 2F1, which means if I subtract these two equations, right, this final minus the initial, then what I get is 2F1 equals 160, which means my fundamental frequency is actually 80 hertz. Well, does that work? Sure, because 240 divided by 80 is 3, and 400 divided by 80 is 5. So I am getting my odd harmonics. So that totally works. So I'm going to say these two are related. The tube is closed, and I know that because I'm only getting the odd harmonics of 3 and 5, and the fundamental frequency, F1, is 80 hertz. Okay? So those two, A and B, worked together. C is just going to use that speed of sound equation to figure out what the length is, but we're given a diameter, so we're actually looking for the actual length of the tube, and we're going to find the effective length and then find the actual length. So let me show you what I mean. We know that F1 equals the speed of sound, and since this is a closed tube, this is over 4L. Well, that L is the effective length of the tube, not the actual length of the tube. So what I have is 343 divided by 4L equals 80. So I'm going to multiply both sides by 4L and then divide by 320. So essentially I get 343 divided by 320, and I get 1.072 meters. That's what the tube is acting how long it is, and that's because it's closed, and so it's got an extra node. That antinode is a little bit further out. So I'm going to use the equation L equals, all right, and this is effective. L effective is equal to L plus 0.33 times D. And so clearly we're going to see that this isn't going to make a heck of a lot of difference, but 1.072 equals L plus 0.33 times 0.05. That was given in the problem. And so if I subtract that off from the 1.072, I'm going to get something that's not very much different. 1.055 meters. Okay, so there's the actual length of the tube. Its effective length is 1.072, and that gives us our harmonics. It's a closed tube, and we figured that out. Next problem says a flute is tuned so it has a fundamental frequency of 440 Hertz at 20 degrees Celsius. The player marches outside where it's 10 degrees. Should the flute be made longer or shorter to maintain its tune, and by how much? Alright, so to tune a flute, you can actually pull the mouthpiece out or push it in a little bit, and we want to know what should we do and by how much should we do it. Well, let's think about what we're told. We're told that at 20 degrees, which means the speed of sound is 343 meters per second, it's tuned so that it has a frequency of 440 Hertz. F equals 440 Hertz. Now, a tube is actually an open, or a flute is an open tube. It's open on both sides. So that means F1 equals 440 equals the speed divided by 2L. So I can say 440 equals 343 divided by 2L, and see that the length of this tube is actually 343 over 880. L equals 0.3897 meters. Okay? The next thing it says is we go outside, should it be made longer or shorter? Well, we want to maintain that 440 Hertz. But now the speed of sound is not 343, it's 331 plus 0.6, or 10 times 0.6, which is 6. So 331 plus 6 is 337. So now I have 337 over 2L. Okay. Well, the new length of my tube, remember I'm adjusting it then, is given by 337 divided by 880. And that means 0.382 whatever meters. So 0.3829 versus 0.3897. How much did it change? It went from 0.383, well, essentially 0.383 to 0.390. We're talking 0.007 meters, or 7 millimeters. So it changes, not a whole heck of a lot, 7 thousandths of a meter, and it got shorter.